Hello everyone, welcome to this presentation on semiconductor materials and fabrication. So semiconductors are the foundation of almost all modern electronics, from smartphones, computers, solar panels, and medical devices. So in this video, I'll guide you through what semiconductors are, the materials used, and how they are fabricated into tiny chips that power our world. So the entire semiconductor industry is rooted in solid-state chemistry. Do you know that? Particularly the behavior of elements like silicon and their transformation through chemical reactions and treatments. Next. What are semiconductors? So what exactly is a semiconductor? A semiconductor is a material with electrical conductivity between that of a conductor like copper and an insulator like glass. So its conductivity can be precisely controlled, making it ideal for building electronic components like transistors and diodes. So semiconductors operate due to their unique electronic band structure, which is a direct result of the chemical bonding and arrangement of atoms in a crystal lattice. So those are, as you can see from the slide, a conductor, a semiconductor, and insulator. Semiconductor materials. Here are some examples of semiconductor materials, particularly silicon, germanium, and gallium arsenide. Here are their properties, as you can see. So the most widely used semiconductor is silicon due to its abundance and excellent properties. Others include germanium, which was used in early transistors, and gallium arsenide, which is better for high-speed applications like microwave devices. Newer materials like silicon carbide and gallium nitride are becoming important for power electronics. So these materials are chosen for their electronic configurations and bonding characteristics for influence, conductivity, and mobility. Compound semiconductors involve covalent and sometimes ionic bonds. Next is why silicon? So silicon dominates the semiconductor industry because it forms a perfect crystal lattice, can be doped easily, and withstands high temperatures. It's also the second most abundant element in the Earth's crust, which makes it cheap and accessible. So it's also important because silicon forms a tetrahedral crystal lattice with strong covalent Si-Si bonds. Its ability to be chemically oxidized to form SiO2 is also a key advantage in device fabrication. So here is the structure of silicon, as you can see, the silicon from the periodic table. Doping in semiconductors. So doping is the process of adding small amounts of impurities to pure silicon. Adding elements like phosphorus introduces extra electrons. This makes it an N-type semiconductor, as you can see from the slide. Adding elements like boron creates holes, or positive carriers, forming a P-type semiconductor, as you can see from the other pic. Doping is what allows semiconductors to conduct electricity in a controlled way. Next is semiconductor fabrication process. So let's now look at the how semiconductor devices are really made. So the process begins with silicon wafers, which are sliced from large cylindrical silicon crystals. These wafers go through multiple steps, particularly oxidation, then next is photolithography, and then etching, and then goes to doping, then metallization, and finally packaging. So each fabrication step involves specific chemical reactions. For example, oxidation to grow the SiO2, acid etching to remove layers, and CVD to deposit thin films. And more importantly, each of these steps require atomic level precision. Photolithography. So a critical step in the process is photolithography, where a light-sensitive material called photoresist is applied to the wafer, the silicon wafer. So a mask blocks UV light in certain areas, allowing us to etch patterns onto the wafer. So this is how tiny transistors, sometimes smaller than 10 nanometers, are created. This is where the transistors come from. So to add, photoresists are polymers that undergo photochemical reactions. UV light exposure causes cross-linking or breakdown, enabling selective removal by solvents and application of photochemistry. Next up is chemistry and semiconductors. So to mention, here are some chemistry in semiconductors. So chemically, silicon has four valence electrons and forms a stable covalent lattice. So doping with boron, 3 valence electrons creates p-type silicon, and phosphorus, 5 valence electrons creates the n-type, like as shown a while ago. So another chemistry fact is oxidation forms the protective layer SiO2 of the wafers. And lastly, etching uses acids or plasmas. Deposition methods like CVD create functional layers. So this slide is to share some core chemical principles like bonding, redox reactions, acid-base chemistry, and thin film chemical synthesis. So next to the process is clean room conditions. So semiconductor fabrication must be done in a clean room where the air is filtered to remove even microscopic dust particles. So a single speck of dust can destroy a chip. So when it a dust can really destroy a chip, single dust. That's why you need to be clean. So engineers wear full suits to avoid contaminating the process. As you can see from the slide, here are some engineers in clean room suit. Here's the chart for particle size comparisons. As small as that can destroy a chip. So packaging and testing. After fabrication, each chip is tested to ensure it works correctly. It's then packaged to protect it and provide connections to a circuit board. The final product is the tiny chip you may find in your phone or your computer. Here are the testing probe stations where you test each chip if it works correctly. And here's the chip in a package. So you see the components. Where are semiconductors used? So semiconductors are everywhere. In your phone, they run your process and memory. In your car, they control the sensors, the braking systems. Same can be said to the laptops. They run your processors and memories. So they're also in solar cells, televisions, and even medical imaging equipment. So the future of semiconductors. The future of semiconductors is really exciting. We're seeing advances in quantum computing, 3D chip stacking, and many more materials. So you can see from this slide, here I have a picture of a quantum chip. This is where a new technology used with the use of semiconductors. While Moore's law predicting chip size will keep shrinking, slowing down, innovation is far from over. So to add more info, future semiconductors may rely on organic molecules, 2D materials like graphene and quantum dot technologies, all of which involve advanced chemical synthesis and molecular design. Thank you for listening. So here's to say that from start to finish, semiconductor technology is built on a foundation of chemistry from atomic bonding to large scale fabrication processes. We discuss what our semiconductors are, the common materials used in semiconductors, fabrication steps, step by step, applications, and future and for the future of semiconductors. So to sum it all up, semiconductors are the building blocks of the digital world. We looked at the materials, fabrication steps, and how they're used in daily life. Thank you for watching, and I hope now you have a better understanding of how these tiny materials power our big world. That's all. Thank you for watching. Bye bye.